In exercise 1413, they would want you to name some epoxides, and the only way this will be different from 1412 is these will have chiral centers. And so you will want to say whether those chiral centers are the left-hand version or the right-hand version of that molecule. Remember, a chiral center is an atom. When you get a chiral center when an atom is bonded to 4 different things. Carbon can form 4 bonds, so if it's bonded to 4 different things, it's pretty easy for it to become one of these chiral centers. Chiral centers are places that are like your hand, and in fact it comes from the Greek word for hand. Chirality is just handedness. Your hand has a bottom, a top, a thumb side, and a pinky side. That's 4 sides. Anything that has 4 sides comes in 2 versions, a left-handed version and a right-handed version. And just like your right hand would not fit into a left-handed glove, the right-handed version of a molecule would not fit into a left-handed enzyme pocket. So whenever you have an atom, usually it's a carbon, that's bonded to 4 different things, you have to say whether you have the right hand or the left hand so that people know what type of pockets it'll be able to fit into. And so that's the new sort of the twist on this relative to 1413. Otherwise, naming the epoxides has a similar process. So the first thing is to find the backbone. The backbone is going to be the longest chain of carbons that you can find without going back or picking up your pencil. Remember that you always think about rings and straight chains separately. So we have this ring here, that benzene ring, and then we have sort of straight chain here. So we're going to think about this separately. Usually you would go with the chain that has more carbons, but if you have a functional group, and here we have an ether, then you go with the smaller chain if that's the chain that has the functional group. So for example, in our straight chain here, it's only 3 carbons, whereas the ring is 4, 5, 6 carbons. Even though the ring has more carbons, we're going to go with this shorter chain as the backbone because it has the functional group on it. A word about what I circled as the backbone. You'll notice I circled 3 things here. There's something that looks a little misleading, and it's this dash. That dash usually is attached to a branch, and so it's really tempting to see this methyl group as a branch. Me is standing for methyl. A methyl group is where you have a CH3 connected. So really, you could redraw this molecule, and you could say, okay, got that oxygen there, and I have just a methyl group there, and then I have my ring. So this CH3 here, which is implied if it's not drawn in, that is the same as that Me, just a methyl group. And so when you're thinking about the chain, that's just another carbon in this straight chain. You would have 1, 2, and 3 carbons, and this whole thing could be considered a chain, straight chain. And so this is going to be your backbone. Now you could number that really from sort of the right top to the bottom. Let me do that in orange. So you could say, okay, this is 1, 2, and 3. Or you can number it the other way. Let me try that in green. 1, 2 here, and 3. Notice that the orange way gives you a lower number for the epoxide, so 1 and 2 for the epoxide, and then it also gives you a 2 for the benzene ring, whereas the green way gives you a 2 and a 3 for the epoxide, and also a 2 for the benzene ring. So you get lower numbers with the orange way, so that's how we're going to number this backbone. So the first step is always to name the backbone as if there were no branches on it. And so if you have 3 carbons, the prefix is pro. In this area, in that circled area, the backbone, we have only single bonds. And so the infix for only single bonds there is AN. So AN. And also in that carbon chain, in the circled area, we only have carbon and hydrogen anywhere. And the suffix for a hydrocarbon a molecule that only has hydrogen and carbon in it, a backbone, is E. So propane is going to be the name of our backbone. Now everything else is going to be named as a branch, and so let's think about these branches one at a time. We have talked about this functional group, this ether in a three-membered ring, being a branch. It's an epoxide. It's a reactive ether because of that ring strain. So epoxides branches are called epoxy. And for the epoxide branch, you give the numbers for where it attaches. You give both of them. So this oxygen here is attached to 1 and to 2. So it'll be 1, 2, epoxy. That's the name for that branch. We have another branch, this branch over here, and that is a benzene ring, that special molecule which is very rigid and very stable because these electrons actually fly around the whole thing. They're not stuck in between two specific carbons because the parallel p orbitals that cause the pi bonds that are written give you parallel p orbitals between the other spaces too, and so the electrons just fly around the whole thing. So that has that special name that we've talked about, which is benzene. But when benzene is a branch, like it is here, it has another special name. When benzene is a branch, it's called phenyl. Phenyl. So here we have a phenyl branch, and that branch is coming off of carbon 2 of the backbone. So this is 2-phenyl. Okay, we take the backbone, that comes last. The epoxy branch always comes immediately in front of that, even if it's not alphabetical. Here it's not, right? P and E. E would come first, so you'd think that branch would come first, but as an exception, epoxides always come immediately before the backbone name because they're so intimately tied to it. And then immediately in front of that, you would have the phenyl. So far what we have for this name is 2-phenyl, 1,2-epoxy-propane. But we are not done. And the sign that we're not done, a hint that we're not done, is that we have these stereochemistry given in the bonds. Stereochemistry is the three-dimensional arrangement of stuff. So normally a bond would be drawn like that, and that means it's in the plane. So it's in the paper, in the board. If it's drawn like this, it means it's coming out at you, and if it's like the solid wedge, and if it's drawn as a dashed wedge, then it means it's going away from you. And usually, not always, but usually those are only indicated, these two are only indicated when you have a chiral center, because it's these that let you determine whether the chiral center is right or left-handed. So the fact that we have those is a sign that probably we have to check for a chiral center. So this atom that has those types of bonds to it, that could be a chiral center. Let's see. Is it bonded to 4 different things? And we look globally here. We have a methyl group, that's one thing. We have a sort of carbon in a chain, fine, that's a second thing. We have an oxygen in this ring, fine, that's a third thing. And we have this benzene ring. So those are 4 different things. So that is indeed a chiral center, and we have to say whether that that carbon at the orange dot is right or left-handed. To find out whether it's right or left-handed, first of all, right-handed would be R, left-handed would be S. We're going to use the Kohn-Ingold-Prelog rules. Kohn, Ingold, and Prelog. Those were the 3 scientists who came up with these rules to determine whether a chiral center is R, right-handed, or S, left-handed. So first we prioritize the groups bonded, the 4 different things bonded to that chiral center, based on the atomic number. That's the number of protons. So here we have, on the top, we have an oxygen. Oxygen has an atomic number of 8. If you look at the top of the box on the periodic table. To the right, we have a carbon that has an atomic number of 6. Here, remember this is a methyl group, that bond is really going to a carbon, and the carbon has 3 hydrogens on it. That's what Me means. So the bond would really be to a carbon there. So here, again, we're dealing with atomic number of 6. And then last but not least, here, we're dealing with another carbon, another atomic number of 6. So we have a lot of ties. But one thing we know for sure is that oxygen is going to get a priority of number 1. It has the highest atomic number, so we can stop thinking about that. Now we just have to worry about what is going to be 2, 3, and 4. So for this carbon on the right, whenever you have a tie, you want to make a table. So I'm going to make a table for the carbon on the right, this carbon at the bottom, and this carbon at the left. And in that table, you want to list the 3 other atoms that atom is bonded to. And I say 3, even though it's bonded to 4 things, because going back, they're all bonded to the same thing. So that's not going to settle any priority claims. So let's think about this carbon on the right. That's bonded to an oxygen, and it's bonded to 2 implied hydrogens. Notice in the table, I put the atoms here in order of descending atomic number. Oxygen has the highest atomic number, 8, so it goes first, and then these have an atomic number of 1, so they come after the oxygen, below the oxygen. Okay, so much for the carbon to the right. How about the carbon at the bottom? Remember, this methyl is a carbon bonded to 3 hydrogens. So what are the 3 things this carbon is bonded to? Hydrogens. They're all the same, so it doesn't matter what order we put those in. How about the carbon on the left? This carbon right here. What is that bonded to? Well, it's bonded to a carbon. That's 1 once. It's bonded to a carbon again. That's twice. And it's bonded to a carbon again 3 times. So that would be considered like 3 carbons. Notice that a double bond is like 2 bonds to a carbon. Okay, now we have these, we're going to compare once we have these tables, we're going to compare them. And you don't look at the whole table at once. You just look at the top row. Only if the top row ties would you go to the second row, and only if the second row ties would you go to the third. So here, in the top left, we have carbon, that's an atomic number of 6. The carbon on the right had an oxygen at the top of its table, that's an atomic number of 8. And the carbon at the bottom had hydrogen at the top of its table. That's an atomic number of 1. 8 is the highest, and so this carbon is going to get the next highest priority. 8. 6 is the next highest after that, and so this carbon in the benzene ring, which is as a branch is called a phenyl ring, that's going to get the priority number 3. And last but not least, the carbon with all hydrogens, that gets the lowest priority, priority 4. All right. So once you have the priority set, if we refer back to these Kahn-Ingold-Prelog rules, CIP rules, once you have this first thing done, prioritizing, go to the second thing, make sure the 4th thing is pointing away. And lucky for us, it is. We'll see in one of the future examples what to do if it's not. If that's pointing away, we go on to the 3rd thing. We go from 1 to 2 to 3. Notice we're completely ignoring 4. So we ignore 4 now. Might as well even erase it. We go from 1 to 2 to 3. If it's clockwise, like it is here, then it's R. If it were counterclockwise, it would be S. You can remember that R is clockwise because if you go from the top to the bottom of an R, you have to go clockwise. Whereas if it were the other way, if it were counterclockwise, it would be like going from the top to the bottom of an S, counterclockwise. So this is R. Because now the stereochemistry always goes in front of the name in parentheses, and because there's only one chiral center in this molecule, we don't have to say where this R is. There's only one place where it could be, on the only chiral center the molecule has. So the name for A here, the beautiful name, is R2-phenyl 1,2-epoxy propane. All right, let's try B. First, we want to find the backbone. It's the longest chain you can find without going back or picking up your pen. I'm seeing 1, 2, 3, 4, 5, 6, 7. The longest one. And so here, the prefix for 7 carbons is hept. Oh, I should say, our backbone, of course, is this numbered chain. The oxygen at the top is going to be named as a branch. So the prefix is 7 for 7 carbons, hept for 7 carbons. The infix, and we have all single bonds here. Every one of these things is single. The infix for all single bonds is AN, and in that backbone also, in the circled area, there's only hydrogen and carbon, so the suffix is E, heptane. Now, we do have a branch. The branch is this oxygen right here, and it's one of those oxygens that sort of come off and immediately boomerang right back, one of those oxirane rings, and so the name for that branch is epoxy. And you want to give the numbers for where that attaches. Now it attaches to carbon 3 and to carbon 4, so it's 3, 4 epoxy. Notice you want to number left to right, or I'm sorry, right to left rather than the other way around, because it gives you lower numbers. Here we had 3 and 4. If you numbered it the other way, you would have 4 and 5. So those are higher numbers. You don't want that. So 3 and 4. So the name for this would, so far what we have for it is 3,4-epoxy heptane. A quaint little name. And that would be the end of the story, except we have chiral centers. And so you would want to be able to give the R or S configuration for each of those. So the chiral centers, where could they be? They always consider the places that have the stereochemistry drawn in. That stereochemistry is usually drawn in to tell you which hand you have at those points. So let's draw this molecule two times, and we'll look at one chiral center at a time. So the first time, okay, so here's one, and let's just duplicate that. Okay, so first, let's consider the chiral center on the left. First, is it even a chiral center? Is it bonded to 4 different things? Well, we've got this oxygen here, we have this carbon here in a 3-membered ring, we have this weird chain. Oh no, I'm only seeing 3 different things. But there's an implied hydrogen there. Remember also, because in a tetrahedral molecule, you'll have 2 bonds that are in the plane, one coming out at you and another going away. So here we already have the 2 in the plane and the 1 coming out, so that hydrogen, which is implied, will be going away. Okay, so we have our 4 different things there. We know that's definitely a chiral center. So let's assign priorities. Oxygen has an atomic number of 8. It's pretty high. Hydrogen has an atomic number of 1. It's pretty low, lowest on the periodic table. Carbon here has an atomic number of 6, and here has an atomic number of 6. So those 2 tie. Well, straight off the bat, we know that the oxygen is going to get the highest priority. It has the highest atomic number. So we'll call that one 1. We also know that the hydrogen is going to get the lowest priority, 4, because it has the lowest atomic number. So it's just a matter of comparing the 2 carbons. Whenever 2 atoms tie, you want to make a little table. I'm going to make a table for the carbon on the right, table for the carbon on the left. So let's first think about this carbon on the right. So this one right here. What 3 things is that bonded to? That is bonded first to the oxygen, next to the carbon, and the third thing it's bonded to, which is not drawn in, is an implied hydrogen. So hydrogen. Okay, so much for that carbon. How about the other carbon? This carbon here. This carbon is bonded to a carbon and to 2 implied hydrogens. And notice in these little tables, I'm putting the atoms in order of descending atomic number. Okay, so once we have the tables drawn, we compare them one column at a time. Only if the first top column ties would you go to the second column down, and so on. Notice this one has an oxygen with an atomic number 8. This one has a carbon with an atomic number 6. 8 is higher than 6. And so this will be 2, and this will have a priority of 3. Oops. So those are our priorities. Now once you have the priorities assigned, you can you want to check. Once you have the priorities assigned, you want to check to make sure that 4 is pointing away. And here we're lucky again, it is pointing away. If it is pointing away, you can ignore it and go to step 3. In step 3, you go from 1 to 2 to 3. And if it's clockwise, then it's right-handed, and if it's counterclockwise, it's left-handed. So we go from 1 to 2 to 3, and this here is clockwise, so it is R. When we numbered this compound, we numbered it from right to left, so 1, 2, 3, 4, 5, 6, 7. Because we're going to have more than one chiral center here, we have to say where this R is. And the R was on this carbon there, which is carbon 4. The chirality always goes in the very front of the name in parentheses, so we will have 4R here. Okay. So then, the next part is to figure out the chirality of the other chiral center. So let's zoom in on this here, and we're going to look for this chiral center here. That's the one we're going to think about. And we know that that is probably a chiral center because it has the stereochemistry drawn in. Let's just make sure. All right, we've got this ethyl group, we've got this oxygen, we have the other carbon chain, and we have an implied hydrogen. Because we have 2 bonds in the plane and 1 going away, we know the hydrogen must be coming out at us, because this is tetrahedral. So that is bonded to 4 different things. It is a chiral center. So after we know it's a chiral center, we want to go to this step 1 and prioritize everything based on atomic number. So this oxygen here has an atomic number of 8. The 2 carbons, this carbon here has an atomic number of 6, this carbon here has an atomic number of 6, the hydrogen at the bottom has an atomic number of 1. So again, immediately we know oxygen has the highest atomic number, it's going to get the highest priority of 1. Hydrogen has the lowest atomic number, it's going to get the lowest priority, a priority of 4. The 2 carbons tie, and so we're going to want to make a table for them. A table for the carbon on the right, and a table for the carbon on the left. Let me erase those 6s so they don't clutter things up. So let's think about the 3 things this carbon is bonded to. It's bonded to a carbon, and it's bonded to 2 hydrogens that are implied. Notice I put them in the table in order of descending atomic number. All right, the other carbon, this carbon here, is bonded to a carbon, this carbon here, that's the one bonded to the chiral center. So that carbon there is bonded to 3 things. It's bonded to an oxygen, it's bonded to a carbon, and a third thing, an implied hydrogen. So when we compare these tables, you look at just the top row, you see that the oxygen here with an atomic number of 8 beats the carbon there with an atomic number of 6. And so this carbon on the left with the oxygen in its table, that oxygen, or that carbon, this carbon here, is going to get the second highest priority. That's higher priority than this other one, which only had a carbon at the top of its table. So this is what we have. We've just found the priorities. Next step, we want to make sure 4 is pointing away. Is 4 pointing away? We've been lucky up to this point. Oh no, 4 is not pointing away. So what we have to do is keep that in the back of our mind. If 4 is pointing out at you, when we go from 1 to 2 to 3, you'll either get R or S. Whatever you get, if 4 is pointing out at you, like it is here, you flip the configuration, you switch it. If you get R, then you switch it to S. If you get S, then you switch it to R. You only do that when the fourth thing is pointing out at you, has that solid wedge. So I'm not going to erase the 4 because I have to remember to keep that in mind. I'm going to go from 1 to 2 to 3. That is counterclockwise, and so you would think that it would be S. But 4 is coming out at you, so you switch this, and it's actually R. So that chiral center is going to be R, and if you remember, so we just found the chirality of this atom here. That atom is carbon number 3, so we'll have 3R. You put that in front of the name. And so the whole beautiful, complete name is 3R4R34 epoxy heptane.